All right, turn it off.
We'll turn it on.
Yeah. Otherwise, I'm confiscating it using it from a golf simulator. Which I can go either way on. So, so you decide which way you want to play this. All right. So let's go here. Do we ever have a 325 dealie? No. Let's go this new Java project CSC325 fall 2016. So we'll do a new class. So let's create our driver class here, and I'll go ahead and have it put main in real quick. And then I'm going to create a class called string 8086. Okay, so we decided that our string class needs to hold a char array of maximum size 64 bytes, right? All right, so we're going to create a private char array called the string, and this is going to be a new char array of size 64. Then we'll have our constructor for this guy, string 8086, and this guy's going to take in a string as a parameter. And then what we want to do is we want to go through this string and load it into the first so many buckets of the string up here, and then terminate it with a $sign, right? Okay, so we're going to go ahead and we're going to do our loop for int I is equal to 0, I is less than s dot length, I plus plus. And we're going to start, we're going to say the string, or this dot, the string at bucket I is equal to s dot char at I. So that'll copy all those elements over. Then we'll say this dot, the string.
You can't store the length in the object.
Oh, okay.
Yeah, you can use the length of the string. Yeah, the string itself.
You could do a while until you get to the $sign.
Yeah, that's what we're going to do when we do the print. Yeah, when you actually use this object, you're printing until you hit a $sign.
Yeah.
That's the termination. We don't store the length of it. In this case, I'm loading our string into the guy. So this dot, the string at bucket s dot length is equal to a $sign. So this is going to add at bucket s dot length, which should be one element beyond where I've already loaded my string into my array. I'm going to put a $sign. So I'm terminating my string with a $sign in my array. Okay, so this is all the setup we need for our string 8086. So we take a string as a parameter, we spin through every bucket of that string, then we grab each char and load it into the equivalent position in my 64 character char array. And then I tag one extra $sign there at the very end. Okay? Now we're supposed to have that terminates it with a $sign. So we're mimicking the 8086 string. Make sense? All right. So now we're going to have a public void, what I say, call it print or display, or I didn't say. Did I say what to call it? What to call the print method? Okay. Is it supposed to print it all on one line or one character?
One character at a time.
Per one character per line, or right next to each other?
Well, you didn't say that.
Print the string, or okay, I got it. I didn't specify. That's fine. All right. So now what we're going to do is we're going to go through the string, doing a system.out.print on every single character we bump into until we finally hit a $sign. Then we're going to break out of the loop. All right, so I'm going to do an infinite loop trick. So I'm going to say while true. Let's do start pause off at 0. Actually, the infinite loop trick doesn't make that much sense here. Then this dot the string dot length, and then I plus plus. So I'm going to potentially go through every single bucket of my char array. All right, potentially. That's what this for loop will do. It'll take I on a journey from bucket 0 all the way up to bucket 63, if I keep going that long. All right, so we're going to ask a question here. If this dot, the string at bucket I, is equivalent to a $, then we're done. Break out of the loop. Else, system dot out dot print this dot the string at bucket I. Okay, and then after we have gone up to the $, if we want to do a carriage return, we can. So I can do a system dot out dot println empty string like that. So that's our print. So our print goes through potentially 64 characters. And as soon as we finally hit a $, we break out of this loop and we throw in a carriage return. So we print the empty string to kick it down a line. Otherwise, we'll just print one character at a time using print instead of println. All right. And then to test this guy here, we're going to say string 8086 S1 is equal to a new string 8086, and we'll put in hello world, and then we're going to go ahead and say S1 dot print, and this should print out hello world and kick it down a line. So if I go ahead and I'm going to do an S2 here, we'll just have this guy say woot. And then S2.print. So this should print out hello world. And then on the next line, it should print out woot. So there's my hello world and my woot. Make sense? All right. So questions about how that guy worked. I am recording, aren't I? Yeah, we're good. Questions about that? Now, what are some downsides to the 8086 string implementation? Can't have a $. So if I want to say hello, well, we'll just throw a $sign in the middle there. So if I say hello space $sign space world for no good reason, I guess, it's going to stop at hello space because I've artificially placed the $sign into my string, right? So the 8086 instruction set is going to mistakenly think I've terminated my string. That makes sense? Okay. So if I run this, I just get the hello, and technically there's actually a space after that guy. But hello space, and then I get a woot because I've broken the way the implementation works. That make sense? That's the sound I make when I clear my throat. It sounds like a bell. So,
I thought it was the bow tie.
that would be cool if she wanted it to flash. What if it also made sounds? Right? You know, like maybe does Mario wear a bow tie? Does he? No. Well, no, those aren't like, it's not either or, right?
It'll wear a collared shirt with it then. I don't think people are wearing collared shirts and overalls. Look up a picture of Mario.
All right. So, any questions on this implementation? Make some decent sense. Okay. So now, do I have my emulator still open here? Let's see. Remind me, Josh. I put the most recent assembly code up on Slack for the 548, right?
Should have.
Okay. So I can dump all this. I'm gonna do it anyways. So it's
Yes.
worst case. I'm gonna have you message it to me.
Are you talking about for like the registry and all that?
Yeah, whatever. Yeah, all that crap.
Yeah.
So I don't think we want to do that in here yet. Okay. Let's get rid of a bunch of this stuff. All right, and I should still have my DOS API open here, right? Yep. All right, so last class, you had looked at the difference between writing a character out versus writing a character out with echo, correct? Okay. When might we want to have echo? Well, actually, it was reading. Sorry, reading a character in, right? It was reading a character versus reading a character with echo. That was what we had not done for this class, but done for the previous class. Okay. When would echo make sense? Why do we have two different system calls for that? One that has echo versus one that doesn't have echo. Go ahead.
Sensitive information you don't want to be displayed back on the terminal is what you would use the not echo for.
Okay.
Stuff that you want people.
Yeah.
So
So
username and password is the easiest. You want them to be able to see their username. You don't want other people to
Yeah.
be able to see that.
now, if I remember correctly, I think our 8086 emulator, the EMU 8086, when you type, it automatically types it in, right? You can see it anyways. It'll echo it, but you'll see it twice. Or does it only show it one time?
We ran into that problem in the master's class where it wasn't showing what you typed in, but it shows it down at the bottom of the screen. That little white
Okay,
thing.
so let's just write it real quick, and then we'll see. So let's go ahead and read a single character in from standard in. So this is our command 1, right? And the character is going to get read into the low half of the AX register. All right, so we're going to go ahead and we're going to load into AH, the instruction we want to do. Then we'll interrupt the CPU and let it go ahead and read in. This is the one without echo. Oh no, this is one with echo. I want the one without echo. Read, no echo. So I want 8. We're going to do 8 first. Okay, so this is the opposite to the character input without echo. It's not 8. What's 7? It's actually the same thing. Direct character input without echo. So this does not check for a for a line break for an enter. Okay, so direct character input would be I hit the button and it read it in. The other one is I hit the button and pressed enter, and that's when it read it in, terminating it. So pick your poison. We'll do so 7 compared to 1. What does 1 say? 1 says read character from echo. So let's just compare 1 to 8 because those seem to be equivalents. But really, 7 and 8 are identical, other than the carriage return thing. Okay, so here's our direct character input. We want 8. All right, so we'll load into AH and 8. All right, so we're going to go into our code segment here. We'll just do it inside of our main proc that I have. So we're going to move AH, comma, that, which looks really cool, right? That's the cooler version of that, or you can just load in 8. What are you guys babbling about?
Sorry, he was trying to get to Terraria running because he wants to, and I was just telling him that he needs to do it.
He's getting video games?
Not right now. He just wants
Oh, yeah.
to do it at some point.
Okay.
I was telling him how he had to do it.
So you're lying.
No,
All right. So we moved AH into, or 8H into AH, but the H here is not necessarily required because 8 hex is the same as 8 decimal. All right, but if you want to make it look legit, you'll say 8H like that. Then we'll call int 21H. That interrupts the CPU, specifically turning control over to the DOS operating system, which then will look in AH and find out, hey, what am I supposed to do? It'll see, oh, I'm supposed to read a character in, paying attention to the character return or whatever. Okay, and we want to see if this actually, what we're interested in here is whether or not EMU 8086's terminal auto echoes or not. So Josh, you said you don't think it does?
Well,
It gives you the thing on the bottom, but you don't think it actually echoes in the thing up top. So
there's one of them that
shouldn't I be able to click on this?
yeah, why isn't it coming up?
the screen.
All right, so it's waiting for some input. So I'm going to put in the letter C. Okay, yeah, it did not echo. So that's with no echo, but we did get the C down here, right, somewhere?
We can't see it, but like if you type
I can't
type
now
in
because
C
it's
now,
yeah.
if you can do it, they're down.
Oh, okay, I see. Yeah, but unimportant for us. That's more their feature. Okay, so that was without echo. So I typed something in, it gave me no echo. I was thinking that maybe this terminal had auto echo turned on so you could actually see you type something. So it's good that it works this way. That way we can see the difference between echo and no echo. All right, so this was our no echo command versus command 1. So I'll move into AH1, which is the echo version of that guy, right? Emulate that.
You said the difference between the 7 and 8 was the 1.
Whether there's a carriage return or not.
So you have to hit enter for you to be done? But does it still only take in 1?
Still only takes in 1. It reads only the one character, the very first character that you entered in. That's actually, yeah, it's not going to read in the carriage return. It's not going to store the carriage return anywhere. We'll see how it can store it when we do some buffered I/O stuff. So let's go ahead and run this, and I'll type in C, and it echoed back out for me. All right, so that's where the echo difference would be. So if you're typing some stuff out and you don't want it to appear on the screen, you would use the no echo. If you're typing some stuff out and you do want it to appear on the screen, which is probably most of the time, you want the echo, otherwise you won't actually get any feedback that you're typing stuff, right? Okay, so 2 different system calls for that. Now, when we're dealing with strings, let's keep trucking here with our system calls. So if we want to write I assume we can see that writing a character is going to work pretty similar to that. So let's kind of move to strings. So if I want to write a string to standard output, which is 9, so we're going to move into AH, the command 9. Okay, but then we need to give it this guy right here. Have we talked about this syntax in here yet? Okay. So first of all, what's DS? What does that register? What does that hold? What is,
Stores the base address of the first data segment.
Okay, so that stores the base address of our data segment. So DS data segment stores the base address of it. All right. Now, so what we're storing inside of DX, so DX is where we're putting our value. We're storing in there the offset of the variable that we want to print relative to DS. Does that make sense? All right, so not only do we need to put 9 into AH, this is what we want to do. We want to do system call 9. It also requires a parameter going into DX, and the meaning of that parameter is going to be a pointer relative to the base address of the data segment where our $ terminated string lives. Okay, so we're going to go ahead and give ourselves a variable. We put our variables in the data segment. I guess we're tabbing here to, yeah, fine, good enough. So we're going to call this, we'll call this guy message. Message will be a data byte, and it's going to be equal to hello world, and I'll put my $ there at the end. Then when I move into AH9, before I interrupt the CPU, I need to go ahead and load into DX, the desired parameter. Okay, and that's an offset from the base address of the data segment. So we're going to move into DX, the offset of offset of message. And message lives inside of our data segment. Now let me open up Keynote. Last time we drew a picture of what the data segment looks like, right? Kind of think of it like a giant array. Yeah, so here was our data segment from, let's see, so here's our data segment. So this guy basically looks like a giant array where one variable, so our variable param1 lived in the first 4 buckets here, and then param2 lived in the next collection. So when I say the offset of param1, like we said right here, what we're doing is we're moving to the beginning, the base address of DS, and then walking into DS, the offset where param1 lives. In this case, it lives at offset 0. So that's what that would return. Okay, so DX is going to hold the value 0. Let's watch that happen. So there's my message. Move into AH9X, move into DX, the offset of message, call 21H. This should do the display thing. So we'll emulate that. Let's walk through this line by line. So right now we have our variables. If I open up vars here, here's our message. These are the hexadecimal values of all the actually this is
Hexadecimal of each letter.
E-L-L. Oh, it's not showing all the elements. If I do 20 elements, it'll, yeah, there. Yeah, whatever. Okay, so this is showing me the hexadecimal value of an H, then an E, then an L, then an L, and an O, so on and so forth. Okay, and if we look at DS, where's DS up here? 700, that's the base address of our data segment. Okay, that's where that guy lives. So I'll move into AH, a 9. So we'll step over there. There's our AH, is a 9. Then I'm going to move into DX, the offset of message. Okay, so DX holds the value, after I did that, 102. What is that relative to? This is the offset address of message relative to DS. I got the value 102.
But doesn't the DX and DS there? No,
Yep, so right now DX in its entirety should hold an offset address of message. What's 102 in decimal? Let's bring this back down to our world. So value of 102. Oop, that wasn't what I wanted that slide to look like. 102 hex to decimal is what? How do we do our conversion? This is the ones place, the 16s place, the 256 place. So that's 258. So this is the decimal number 258. Okay? That's an offset address. Now, DS was at 700. So what we're advertising there is that 958 is the actual base address of our message. So what do you suppose is happening inside of DS prior to that? Do we have more memory stuff up here? $700. All right, so here's our base address eventually. Take smaller hops. I might not be able to get right to set up. All right, so here's 700 offset 0. So we have some values in there, CD, length 2, and we have 20. So there's some values that are in there. Our offset here was DX 0102. Is this the number, 102? What would we expect to find at the very first bucket if we give an offset address of DX? We'd expect to find our H, right? What's the value of H? Was it 48, this guy? Because this is the uppercase H. Okay, so it should be a 48 H. We see that right there, right? So there's our 48, there's our 65, there's our 6C. But that started at memory address 7. Let's go back up here. We had 7100, 700, 700. So the base address of our data segment is way up top there, right? So at 700. Yet the first place we see our value for our message is here at 7102. 102. That's the offset off that. What do you suspect is happening between 700 and 7102? What kind of crap goes in there? If you think about this from a, I'm an assembler. I just processed a assembly, some assembly instructions, and I need to build a variable environment. And I've taken up 102. Let's just use decimal numbers. So I've taken up 102 spots of memory for something before I finally got to real stuff. What do you suspect actually goes into that that memory for your data segment? So we have a couple of things before that. We scroll all the way up here. Won't take that long, and this will be more precise than I would be. All right, so this is what's actually stored in there. We have a CD at 700. We have a, well, this is base address 700 offset 0, offset 1, offset 2, so on and so forth. Okay. These values are numbers that are telling us information about our data segment. How much memory it's taking up, how much stuff is there. Everything else that is in here, so when we look at our data segment here, all we have inside of data is one variable. Oh, perfect. Will that jump? Oh, nice. So I can get to it just by clicking there. Although that's 7100. That's not the base address of it. So I need.
Just type it on top, right?
Oh, I can do here.
And then click. You're at 700, 100. And the base address was 700.
Offset 100. So I need to do
All zeros.
that. Gets me there.
Yep.
Okay. Let's see, where is the value I'm looking for? Okay, so our code segment and our data segment are both 700. We saw that last time because this is model. Actually, that should be for model tiny. I think if we take the dot stack out, it'll act right from those, because the different model numbers tell us the different whether our data segment plus our stack segment or plus our code segment to get 64K each or combined 64. What kind of memory footprint we get here. Okay, but in any case, when we're assembling this and we start with we have to build our variable environment effectively, there is information we need to keep track of before we actually get to our data. All right, so when we ask for an offset of message relative to DS, we're getting a 102 because that's where message actually starts relative to the base address of DS, which is 700. That's when we actually started seeing those values in memory. Make sense? So if we were going to connect that to a picture here, we would see a whole bunch of buckets prior to this that are part of the structure of how our data segment actually works. Okay? Organizational stuff, if you will. All right, so I was single stepping. So here's our interrupt, and there's our hello world. Went all the way up to our $. And if we want to see the equivalent to what we did in our Java code, if I go ahead and put a $sign in there, and then we save this, and I emulate that, and then we run, we get our hello space. So our Java program seems to work the same as the emulator works. Okay, so the $ is kind of out of the question here for being able to house it within DOS's, the 8086 version of DOS, well, 8086 compatible version of DOS, house that inside of what it calls a string, $ terminated stuff. So if we wanted to print out a $, how would we do that? Well, in Java, we would do escape character, right? Saying, don't treat this as a string termination, something or other. Okay. Well, if we're trying to MacGyver this we watched the MacGyver episode. If we're trying to MacGyver this based on what we know in here, we know that strings are treated specially, right? Well, the 8086 DOS version of a string, it says, look, if you want me to treat this thing as a convenience for you as a string, I'm looking for a $ finishing that thing, because strings didn't really exist. But as human beings, we like to print out words and sentences and things like that. So as a convenience to us, printing out a whole bunch of characters as long as they're not $ is helpful. How do we print out a bunch of stuff that, how do I print out the string hello $world and actually have it show up as this output?
Check to see if there's more afterwards.
Okay, well here, let's go back over to our Java implementation. I want to update my Java implementation so that hello space $ space world prints out hello $world.
I would do a count of how many $, although I can't, you're not going to do that with the Java string variable, are you?
Well, it's not a Java string variable. Over here, it's a char array.
Yeah, I know, but when I bring the string in, I would check to see if there are any $ in it already. And then I would start a count that says like $ count.
I see what you're saying. Yeah, that's not gonna fly. Yeah, we're using the bring it in as a string as a convenience for us to test this. Yeah, realistically, it's stored inside of our character array. So I have a character array that's 64 characters wide as a max. We just arbitrarily pick that to keep our life somewhat reasonable here. I'm loading into it a subset of that, the hello space $ space world $, right? So I'm going to have two $ in there. If we were to look at this guy afterwards, if we were to print out those individual characters, it's going to show HELLO space, then a $ space WORLD, then another $. So we actually had two $s in there. But our print method right now terminates on the first $. I want to write a version of our print method, we're going to call it an upgraded version of our print method that will print out everything in our string. Print out everything in our string, including $, but not the last $. So our strings are terminated by the last $. How would we pull that off? Go ahead. Okay. Well, this isn't going to be efficient. Let's just start with that guy. All right, so I'm going to steal this for another slide. Nope, it's not the one I want. So we have HELLO space $ space. Oh, I just put a lot of stuff into that character. W O R L D $. That's what actually has gotten loaded into our character array that in Java we called the string. Right? So this is the string. Except there's a bunch more buckets over there, even though I only have 2 extra ones shown here. So that's my string, which has a base address of 100, which effectively points here. Okay, and our current version of print starts at bucket 0 here and walks through and says, is this a $? No, print it. 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 Yes, breakout. I wanted to print it, 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 and then notice that this is the last one and breakout. So we want to keep in our mindset that this guy's going to work the way that memory works. So we're staying in the 8086 world, okay, from a memory structure perspective, yet we're writing the algorithm initially in the Java world. And then we'll write the algorithm in the 8086 assembly world. So if I show you a character array that looks like this, where all the memory after this guy is empty, where is the position of the last $? How would we calculate that? Okay, let's. All right, so let's do. I'm going to throw an A after this and a B after this. Okay, so I'm filling out some more random stuff in memory. So if we're thinking about this in our 8086 memory,
Oh, that's another array or something.
it's something. It's something that doesn't belong to our something, right? So if this is our .data segment, okay, so this giant array, our string lived here, and the next thing came after that. So there was values there. So this may have even been the string A, let's say, that would look like that. So I could have in my assembly. I can do S2 is a data byte that is A with a $. So it's another string. So our data segment in this case would be hello world with the stuff in it, followed by another string, which is A $. So if I were to put in the offset of S2, it would, relative to DS, give us this 114. That tells us where that variable begins. That make sense? So in Java, how would I take a character array that is my representation of a string and store in it the position of the last, how would I figure out the position of the last $? Can we walk a character array backwards? In Java, can we walk it backwards? So I can go where the last bucket in the character array is. What's the last bucket of our character array in this code? What's the bucket position? -1. So 63 in this case, s.length -1. So I can start there and start walking towards the beginning, saying, are you a $? Are you a $? Are you a $? Are you a $? And finally, when I hit a $, what do I know about that $? He's my last $. If I'm walking here, so in our world, these are all empty, right? In our character array. Are you a dollar sign? No. Are you a dollar sign? No. Are you a dollar sign? Yes. You were my last dollar sign.
Oh, you're saying.
That's the actual string termination, right? That dollar sign's the actual string termination, not this guy. Okay? So, I know that that guy's going to be the end of my string. But I want to print this guy out forwards. How would we do that in Java? What's the algorithm that I can first identify the last dollar sign? Then, now that I know what actually is the string termination dollar sign, I want to print everything but that, but forwards. I want to say hello space dollar sign space world, not those guys backwards. I don't want to say DLROW space. Make sense? So how would I write that in Java? What's the next step?
Well, you would take that location.
Yeah, so I mean, start off with the logic. So we'll call this guy superprint.
Well, okay. Well, I guess in what you would do for an assembly is you would recognize or see that location, store that in a register.
Well, we're doing this in Java first. Yeah, we're going to do the Java algorithm. Because then we want to see what it would take to convert that to assembly. Because we know it ultimately is getting converted to assembly, right? I mean, when we compile it, that's what's happening. It's getting turned into a low-level language. So we're going to find the pos of last dollar sign. So we'll start a for loop. Int I is equal to this dot the string dot length minus 1. So that's the last legal bucket. Keep going as long as I is greater than or equal to 0. And I minus minus each time. And we'll create a little variable here called last dollar sign pause. And we'll start this guy off at this dot the string dot length. So it'll be off the end of it to begin with. All right. So that as we're walking through that character array backwards, we'll keep asking the question if this dot the string dot char.
Well, do you need to do the loop? Because the end should always be the string termination key.
Oh no, I have 64 buckets in here. Yet I'm only using a small portion of them to hold my string.
But the last bucket of the string dot length minus 1 should always be the string.
This isn't the string dot length. This is my char array dot length.
Oh, okay.
Yeah, I got this giant memory space. Giant being 64 characters in this case. And I have a much smaller string I'm storing in there.
Then you're gonna get a no pointer exception.
Why?
Right?
If I say this dot, if this dot char at, this dot the string char at I is equal to a dollar sign, then we're going to set last dollar sign pause equal to I, and we'll break. This dot the string, oh, this isn't char at. Yeah, this is that bucket I. That's it. So I'll go off the end of the last pause, or I could actually say -1. Maybe -1 makes more sense there. Just kind of saying this isn't a real pause. So we'll start last dollar sign pause off at -1. We'll start at the end of our character array, which presumably is at least likely not filled all the way up, right? Right now we have hello dollar sign world, which is far less than 64 characters. So I have a whole bunch of fluff at the end of that character array. So I'm walking through all that fluff until I finally get to a dollar sign, which is the very last dollar sign in there. Make sense? All right. So that's what this guy does. When we come out of this for loop, we have stored in last dollar sign pause the position of what's actually our string terminator. Make sense? Okay. So now I have that. But now I want to print out my the elements of my array, okay, elements of my string, and that's where I want to start making a disconnect between the idea of an array and the idea of a string. Okay, so we're going to have our disconnect there. Now, as I'm doing this, I want to now print out the string up to, but not including that position of our last $sign forwards. I want to write this guy forwards. So I just finished walking backwards. Now I know where the actual end is. Now I know where the actual beginning is. That's bucket 0, or in the assembly world, that would be the offset of this variable, right? So that's bucket 0 of that guy. So I can start walking between that memory address and this memory address, the one we just calculated, printing out each character. So now I can say for int I is equal to 0, I is less than pause. What did I call it? Last pause, last $sign pause, last $sign pause, I plus plus, and then I'll say system dot out dot print this dot the string at bucket I, and then ultimately I'll say system dot out dot println the empty string to kick it down a line. All right, so that's our super print. So if I come out here and I say s1 dot super print, now I get our hello $sign world. They got the whole thing. What would be challenging converting this code, this algorithm here, into assembly? What struggles would we have with that? Based on what we know about the data segment right now.
You're saying converting this to assembly?
Yeah. And big picture, don't try to convert it line by line right now. What advantage do we have here in Java, or you can look at it, what disadvantage are we going to have in assembly?
We don't have a string. Oh, no.
We didn't have okay. We didn't have the string length. We don't know where the end of the possible memory space is for this guy, right? We don't have that. In here, we artificially created our memory space. We said, look, we got space for 64 chars. That's what I'm going to give you for storing your strings. All right? Now, you could use that, but I know where I know the very last place that I'm allowed to look, right? And then I can walk backwards from there. Where's the last place? If we go back to the assembly example here, we go to message, and similarly S2, we drew the picture in here. So this was A, then $sign. How do we know that the last place to start looking is right here? We can walk through memory backwards in assembly. But the problem is where is the end of that memory? Say this again?
You're saying at the end of the data segment?
Okay, so that's kind of where I want you to go with this. So if we go to the end of the data segment, we are going to have to be traipsing through other variables, right?
Yeah.
That might be $sign terminated or something like that.
Is there a way we can get the offset of the next variable stored there? But even then, is a data segment contiguous memory?
Yeah, it is.
It is. So then we could take the offset of the string we know, and we start there, and then we add on the offset of the second string or whatever the next thing in the data start, and we start it there.
Okay.
And then go backwards.
So let's first of all, I like that. This is the discussion I'm looking for. Okay, so we're in the right ballpark now. How do I know the offset of the second variable? Generically. I mean, if we look here at this code, the offset of the second variable is, it's the offset of S2.
Yeah.
Well,
So
we're writing generic code here. How do we know, A, the name of the second variable to begin with, right? How do we know? We don't know where one begins and the next one begins. We're kind of reliant on that information coming from that pre-processing of our data segment. It's keeping track of all those little offsets. We don't even know how many variables we have if we're down here in the code segment. Okay? So we're kind of having to play MacGyver with what tools we have laying around us. Now the hint here is going to be that we're going to have to store the length of something in another value. We're going to have to keep track of our length. That make sense? This is why it became kind of debilitating for us. I mean, it wasn't so horrible in Java because Java gives us a lot of tools for asking the length of things and stuff like that. But what if I said here that, oh, you are not allowed to know what the last legal bucket of the string is? So now we solve this exact same problem where this line of code is not allowed.
Is going until you hit null a bad thing?
But you wouldn't necessarily hit null.
You would just
We
try
would
to
do right
decide
after.
now.
In this we would hit null. 'Cause we're doing
In this we would. But if we're thinking about our data segment, you're going to end up just running right off. It's like, okay, here's the, we're on variable 2 now. We didn't know that.
I know, we should
Yeah.
have a variable that signifies the end of the string. I'm making a joke.
Well, I mean,
That's what we're trying to do.
yeah, I mean, it's not necessarily a horrible idea. We can either store the length of the string.
But then we encounter the same problem, where if we count until the $, then who knows if that's in the middle of a word or the end of the word.
Well, I mean, let's say that, let's go back here. Let's say I just called this guy end. Okay, and end was just the empty string followed by a $. All right. Actually, it doesn't even matter what we put in here. Here we can. We'll just set end to -1. Really doesn't matter what we put in there because what are we looking for? I just want the offset of end. I know we're done with our variables at that point. So we could even call this guy end message. End message would be the last legal bucket in, well, one pass, the last legal bucket in message, since these guys are contiguous. So this is the next variable after message called end message. And this guy's offset would be right off the end of where this guy finishes. So I would know where to start.
But isn't that, don't we solve the same problem of how do we know that that's the last one, or how do we know?
Oh, in this case, we wrote it that way. Yeah. We're having to deal with given information. Yeah, you're right. So if I need to know how long this guy is, because I mean, what I want to emphasize here is that we have a limitation dealing with DOS's built-in display string function. It might not be as malleable for us as we want it to be. Now, having said that, could we just go through life never actually trying to print a $? Wouldn't be the end of the world, right? Okay, if we really needed a $, to be like before, some amount of money, couldn't we just do a direct print of a $? We just print a single char, $, right? Yeah, I mean, I can go into our DOS API here. We'll scroll up, and we have the thing to write character to standard out, which is bucket 2. So can't I do move AH 2H? And then where does it want me to put that? DL, okay. So we'll move into DL. What's the hex value for a $?
No, hang on.
Hex ASCII value $. It's 24? Okay, that's fine. Cool. Okay, so we'll move into DL, the value 24 hex. We're good? Okay, so we'll move into DL, the value 24 hex, which is the ASCII value of the $, according to them. All right, then we'll move into AH2H. We want to print a single character, and then I'll do an int 21H. And then we'll do our whole hello world thing here, which is just going to do hello space. But before that, we should get a single $sign because we printed out a single character, which doesn't rely on the magical $sign termination string thingy. Make sense? So we'll go ahead and emulate this. We'll run it, and there's our $sign at the beginning. Okay? So it's not that $signs are off limits. It's that $signs are off limits in terms of using the built-in DOS API write string to screen convenience method. Right? So what options could we have? If we wanted to have something, the ability to write a string out that had $signs in it, could we rewrite that function? I mean, could we just decide, you know what, the whole 9H thing it doesn't work for me. I kind of like my own version of being able to write a string out. We could walk through memory, right? Yeah, I mean, it's not a big deal. Okay, so, but what we'd have to do is we'd have to come up with another way of knowing the end of the string, which effectively means picking a different termination character. Could we pick better termination characters? What's a good termination character for a string?
Something that's never used besides for that.
Or you could do the enter, which is
You do the who?
enter when they click enter.
Okay, carriage return. Okay. What was that? Is that 0D?
0, yeah, 0x, 0d.
So we could pick a different termination character, right? Something that is less used or never used. You know, something like that. We can go into Ascii and find one of the playing cards and say, oh, that's the term. I mean, chances are you're not going to write
Then you have to write that on there. Oh no, you wouldn't. That's just what they use.
You'd have to add it. Yeah, when you write your strings, you would just terminate all your strings with that value. So the value would look like, well, yeah, let's see. Don't we have a? Do we have a list here somewhere? Oh, we get to it. Is it view?
Or
Ascii codes, yeah.
Oh, it's at the top.
I found it.
Then you can
I did it in view.
click on it.
All right, so I just want to find oh, here, we can go with null. We can have null terminated strings. So this is hex.
I feel like null terminated would get messier now.
We can do mu terminated. Copyright terminated.
Definitely copyright.
Copyright terminated all our things with just the copyright symbol. It's like, look, somebody tries to steal your code. You go, look, it's copyrighted everywhere. All throughout my code, I've copyrighted. I copyright strings. I terminate my integers with copyrights. All right, so this guy probably hasn't. Is this just plus minus, or does he have another weird pagan name or something? That guy seems kind of weird, actually, to me. Ooh, 1/2, 1/4.
When you do a cross, you get the Christian world.
Ah,
Ooh.
is there one? Where's the cross? Ah,
Is that what that actually is?
that's bonus points for this guy. All right, so we're going to terminate all of our strings with the cross. All right, so that is, oh, that's beautiful. So that means we're going to terminate every string with a $sign, I'm sorry, with a hex 86. Hex 86 is the cross. Oh, I love that. It's perfect. All right, so close this guy. I think that will do it. Pretty sure that will do it. Get rid of this because we're abandoning that function because it's a crappy function. Doesn't do what we want it to do. So let's just make sure that 86H will print out. Let's just make sure it's discovered as a cross in here. So we should just get that single character when we run this. Yep, there's our cross. So we're good to go there. All right, so what we want to do is, this guy is effectively a collection of chars, right? He's effectively a collection of chars. We can get the offset of this guy by looking at the offset of message. Oh, I'm not in that. Okay, so we can get the offset of this guy by looking at the offset of message. But then I need to walk through this guy, displaying one character to the screen at a time until I hit a cross. And then I know I'm done. Make sense? Okay, now we can rely on this guy being a cross initially. So we're going to go ahead and, first of all, we have our display char code here. I'm going to go ahead and create a new function. So let's call this guy, let's see, we'll call it superprint. This guy's going to be a proc, np superprint. We'll make sure we get our return here at the end. So there's our return. And what we want to do is we want to, somewhere we're going to have to say the guy that we want to actually print. So maybe we move into dx, the offset of the value we want to start printing from. Okay, so maybe up here we move dx offset of message. So then we'll have the base address of this variable. We know where we're beginning. So we'll have this guy assume the base address is in dx of what we want to print. So that's where that's how we're passing our parameter. So we're loading into dx ahead of time the offset of the message we want to print. Okay? Then we're going to go ahead and we're going to call superprint. Okay? Call superprint, and that's going to move our guy over here. Have him pick up where we left off. Okay? We want to keep walking through our code here until we hit a cross, which what was 84? 86H. Okay, so in order to do this, we're going to have to mess with labels. Okay, so we're going to have a label in here called begin. Let's put a label in. We'll throw this guy as begin, and I'm going to have another label called end inside here.
That's not a good idea, is it?
Is it a keyword? It is a keyword. We'll do sp begin and sp underscore end. Superprint begin, superprint end. Okay, this is ultimately where we want to get to, is when we hit this. And we want to keep looping back up here. We actually probably could just do this with a return, but whatever. We'll leave it like this. So we want to have code under this label. And what we need to do is we need to look at the value that is inside of that the current memory address. So we need to take our current memory address, which is in, we have it stored in dx. All right, and we want to say, is the value that lives here my terminating character? Does that make sense? So I want to do a compare. So let's go back to our documentation here. Yep, but we want to. So here's the CMP command. So we can compare two registers of the same size, and what it does is does subtraction, and the 0 flag will get set if they're identical. Compare can be used with a register and memory, with memory and a register, with two registers, with memory and an immediate, and with register and an immediate. So we can look at the current value of the register and compare it to an immediate value. Does that make sense? All right. So we want to compare DX with 86H. Make sense? So that's what we want to do. If that guy is, if this is equal, which we'll know is the 0 flag will be set. And if that's the case, then we need to start using our various jumps, right? So we have no way of, well, we sort of do, but for right now, we have no way of looking directly at our flags. So we're going to have to jump based on our various flags. So one of these things is called, is it JMZ or just JZ? Isn't JZ a singer guy or something? It's a guy, right?
The singer guy.
JNZ and JZ.
Jump, well, jump if not 0 is JNZ. Jump if 0 is just JZ, I think. Here, we'll see really quick.
JNZ. JZ.
Yeah, there's JZ. So JZ says jump if 0. So if you, right after you do a compare, you can then jump to a label. Okay, so we're starting to mess with labels. You can jump to a label in the event that the 0 flag was set. That means they were equal. Make sense? Okay. So we can come in here and we could say SP, well, actually what we want to do is if they were equal, if we did find our $, what do we want to do? We want to jump to SP end. So JZ SP underscore end. So after doing a compare, if the contents of DX match the contents of 86H, then we want to jump to the end. That's our terminating character. Make sense? Otherwise, if we're still kicking, that means that we are looking at something that is not a cross. Make sense? Okay, and what do we want to do? If I'm looking at a memory address that's not a cross, then I want to print that character. Okay, well, so we're back to our DOS stuff. Write a character standard output. It's going to rely on DL. Okay, so we probably maybe didn't want to load stuff into DX. So let's use AX. So we'll move into AX, that offset. We'll compare AX to this register. If we're still kicking here, we want to move into DL, the character that we want to print. How do I get the value at a memory address? So the memory address is AX, right? So I'm pretty sure offset always returns a 16-bit value, even though we know it'll be in the low half of that. So we know since this guy is going to be a, actually we don't necessarily know it'll be in the low half of that. We know AX is the full place. So I want the value at AX. Okay. But I need to ultimately get it into DL for the character. So we can use move, and I want to move into DL some value. Now, what's currently stored inside of AX? This is an address, which means that this line right here doesn't quite do what we want it to do. I'm not comparing the character at AX to this. I'm comparing the address to see if the address matches that guy. How do I get the value at a position? So I'm going to take out my call to superprint here. All right, well,
if you did do message, it would be H every single time.
So I'm going to move into DL the value of, and actually, can we do?
Yeah. Yes, because the value of it is.
I guess we're just assuming it'll work. Okay. So that says give me the value of that. Then move into. So we can't use. We need AH for our system call. So we're printing out a single character, which is 2, right? And then do an int 21H. So if I'm moving into CX, the offset of message, which should be the memory address of the very first character in message, which should be a capital H. That's what we're looking at here. Okay, so offset of message should be the memory address of that dude right there. But it's the memory address, not the dude itself. Then I want to get the value at that memory address. Yep. So I'm going to load the value, and I'm a little questionable whether I can load that into that because there's.
It's an 8-bit value.
We know that it is, but
You can't.
maybe it's because they can't confirm that it's not, that it's okay. All right, so we'll move the value at CX into DL, which is what the DOS API dictates. If you want to print a char, move the char that you want to print into DL. Fair enough. Then move into AH2H and then call the interrupt. So we hope this gives us a H. Let's see. Yeah, probably no 0. Have to move into a memory address, maybe? Data byte?
What was the error?
Well, I mean, the error it's giving us is that it thinks that the second value is the wrong parameters for a move because it can't identify what this guy is because it needs to be. We have to move it into a register first. We can even move into a data byte, so we can do. Call this val db question mark. So we'll move into val cx, then move into dl val, then try to print. Because this guy was not an immediate value, we had to. Where's val cx? How do we get the value out of that? Because there's no guarantee that this guy is an address. All right, so we're gonna have to do the array discussion first then to make this work, which means then we have our buffered input. Status. Okay, so let me do this. What was the last thing we read in the book?
We finished 2. I think. I thought. Oh, no, we didn't.
It's just multiplication and division is the last thing.
Oh, which was in arithmetic.
I think we skipped 2.
Yeah, we did. We're somewhere in the middle here in terms of doing instruction stuff. Okay, so let's read 3, 5, 6, and 7 and be ready for a quiz on Tuesday. Because I can't give you the programming assignment yet because we can't read from a bucket until we do arrays. 3.5 through 3.7 and be prepared for a quiz on Tuesday. All right, I'll see everybody on Tuesday, and I think we'll probably end up covering arrays on Tuesday then.